Okay. Okay, our last presentation before lunch is Ryan Plauché on the Rust programming language, and then we're going to have another presentation on Rust just after lunch. So Rust is really gaining a lot of popularity, so it's good that we've got a couple of presentations on that here at the workshop.
Great. All right, good morning. My name is Ryan. I'll be talking about the Rust programming language. I realize I'm the presentation right before lunch, so I'll try to be fairly expedient. If there's anything in here that y'all would like to hear more about in detail, come grab me afterwards. I have a lot that I'm going to try to cover relatively quickly. So this presentation is going to try to answer 4 different questions briefly. What is Rust? Why do we, as in myself and the company I work for, use Rust? Why do we like using Rust? And then, why should you hesitate about using Rust? I want to try to give a relatively unbiased or balanced view of Rust. I'm not here to just say that Rust is the best. That's not what I'm here for. I'm here with an open mind as someone who's used Rust, hoping to present a relatively open-minded view. I'm not here to bash other languages. I think it's great that there are other languages in play in this industry, and I just want to present Rust as another option for people to use. I would say I'm not here to debate which language has the best mascot, but I think it's pretty hard to argue with this one. So a little background on me. I'm a software engineer. I work for a company called Cubos, and we are a pure software company based in Dallas. We develop ground station software for mission ops, and then Rust-based flight software, which is what I work on. So this software is now primarily written in Rust, which is, I think, great. The little C code still that we integrate with. And if you want to take a look at it, it's all up on GitHub at github.com/cubos/cubos. So you can go see our Rust code if you want to see what that looks like in a relatively production environment. So we'll start with what is Rust. So in 16 words from the Rust website, Rust is a systems programming language that runs blazingly fast, prevents seg faults, and guarantees thread safety. That seems pretty good to me, so maybe we can just stop with that and go to lunch. Yeah, so Rust is a systems language at the level of C and C++. It came out of Mozilla in their efforts to figure out how do we do software development better on a product like Firefox, where there's so many lines of C++ and all these threads running together and a lot of different engineers having to coordinate their efforts. How can we do things a little better, bring people on quicker, write this code in a way that causes fewer issues? So a few high-level features or things about Rust. It is a statically compiled language. So with the compiler, you can produce your static libraries, your dynamic libraries, or even an executable. This is not an interpreted language, and it doesn't run on a VM like other scripting languages. It is statically compiled. It's LLVM-based, so it's pretty exciting to hear from Daniel about LLVM support for the Leon 3. Maybe that means one day there will be Rust support for the Leon 3, which could be pretty cool. Rust is a strongly typed language, similar to your Ada, so the compiler doesn't really let you get away with too much when it comes to fudging between types, which I appreciate. It means the compiler really helps me write better code. It's also fairly expressive in its type system, in that with things like enums, you can actually insert data into your different enum variants. And there's also support for generics, and that's incorporated into how you can build types. So you can build nested types or types that incorporate generics, so they're parameterized. So I find it really helps me express what I'm trying to create when I'm creating my types. Okay, this is one of I feel like it's one of the big things about Rust that people talk about. It's definitely huge, but maybe not the only good thing about Rust. So the Rust compiler has this thing called the borrow checker built into it, and the borrow checker will trace the lifetimes and the ownership of the data in your program or the memory usage in your program. And it will let you know, hey, someone else owns that data right now and you're trying to access it. That's not very safe. I'm not going to let you do that. Or, hey, someone else has already, like this data has been freed, so you shouldn't be able to read that. So that's now a compile time error. So the compiler kind of forces you to write code that is considerably safer from the ownership perspective. And for a lot of people, that's a huge win of using Rust, in that it forces you to write safer code from the whole reference counter pointer perspective. And a consequence or a win of that is that Rust has a static garbage collector. So because the compiler can verify at compile time when data falls out of scope and when the reference count has gone to 0, it doesn't need a runtime garbage collector to go through and sweep through all the memory and see who is or isn't holding on to data. We know after the compilation is done when these things fall out of scope, so we can just release them at that point. So we don't have the runtime overhead of a garbage collector, which is great. And then Rust has a really rich standard library. I feel like every day I appreciate it more and more as I try to figure out, okay, how do I read this file in this way, or how do I interpret this string data in this way? I can typically find something in the standard library that will allow me to do that. So there's a lot of tools there that the community has spent a lot of time building to really enable developers to move quickly, and I really appreciate that. So why do we, as a software company, use Rust, or as a flight software company, use Rust? Well, it kind of started here 2 years ago when someone asked me this question. I was presenting about the flight software I work on, and at the time it was all written in C. And someone who isn't here, but I think a lot of y'all probably know him, Dr. Carl Brandon. He's a pretty strong advocate of Ada. And after my presentation, he asked me this question. And at the time, I didn't have a really good answer, but it really made me think about how do we account for this, and this is something that's acceptable for us to carry in the future. And while we didn't end up going with Ada, I think he might be happy to know that asking that question really influenced my thinking and really set the gears turning in our company. So as I brought this question to different people that I worked with, and we started to think about our customers and our product. So the product I work on, it's not just flight software, it's a framework for people to use when they build flight software. So it's important for us to consider, what is the customer's experience like? And for us, a lot of our customers are new space startups where maybe their software background isn't super strong. So while C may appear to have a relatively low learning curve when it comes to new software developers, I think it can be a pretty dangerous learning curve if you don't know what you're doing. If you don't have someone who's more experienced there guiding you and checking your code. And I can't necessarily do that for my customers, so I want to do what I can to provide them with the best experience. Rust, I would say, has a pretty steep learning curve, but it's a relatively safe one in that while the compiler may be mad at you a lot while you're learning the language, it's mad because it's protecting you from doing things that would harm your software. So it seemed like it was worth it to put that cost on the customers of having to learn or deal with this potentially more difficult language to protect them from problems that they might unknowingly cause if they were just writing in C. Kind of the last thing for us as a company that pushed us over into Rust was using GraphQL. So GraphQL is it's a strongly typed query language that we decided to use as a protocol between our services and our architecture. And we found it worked really well with Rust in that as we're describing our GraphQL schema using the GraphQL library for Rust, the Rust compiler can validate all the types in our GraphQL schema. So we get the extension of this strong type system across our protocol schema, and that was just a huge win for us. We also found that for C, there weren't really good GraphQL libraries out there, and there wasn't a good GraphQL service already built. And we didn't really want to build that ourselves and be the owners of that when that's not our core business. So kind of pushed us over the edge to move to a language that did support that and gave us a lot of other wins. All right, so now I'm going to talk about some of the features of Rust that we have really come to appreciate as we've spent the past year developing in it. And the first one is error handling. Rust does such a good job of making it just a joy to create errors and return them and handle them. It's not done through exceptions, it's more done through standard return types. So when it comes to defining errors, all right, we can have a pretty standard enum like you would in C. This should look very familiar to everyone. But as we dig more into the Rust type system, we can start to embed data in our errors. So if we have a device command where we can turn on or off an LED, and we can embed that LED number in our device command. Well, if that command fails, we can actually embed the specific command that failed in the error. So as those errors populate back up, we can collect a lot of information about what's going on in the system for future logging and diagnosis. Now, when it comes to returning errors, Rust does something pretty cool. So this is going back to the expressive type system. We have this enum that is parameterized over two different types. We have type T, which is the data that we want to return in our nominal case, and type E, which is the error that we want to return when things fail. So this function returns a type of result, but that result could hold an unsigned 32-bit integer or a device error, depending on whether things went good or bad. We're not dealing with multiple return values here. It's one return value, which is that enum. It's just the variant changes based on whether things went well or whether things didn't go well. And then you can see we have these, so the OK variant holds the data in the good case, and then the error variant holds whichever error we needed to return in that case. And then when it comes to handling it, so when we call that function, Rust has this nice match keyword that lets us go through different variants of whatever data type we're handling. In this case, since it's a result, we know there's just the OK and the error that we need to handle. So if it's good, we bring out the data. If it's bad, we continue to propagate that error up until whoever is handling errors gets the chance to take a look at it. Now, the creators of Rust saw this and they thought, okay, this is like a really common pattern. Can we make this a little easier for people? Yes, we can. So what you can actually do is if you just put a question mark at the end of a function that you're calling that returns a result, it will just pull that data out for you if it's good, and if it's not, return the error up. So it's kind of a shorthand for that match OK error. They've just done a really good job of making it super ergonomic to handle and create errors, which we've really appreciated in our development experience. Okay, traits and generics. So traits are Rust's mechanism for defining abstract behavior. You could kind of think of a trait as like an interface in the C++ world, or the object-oriented world. So I define this trait. Let's say I want to be able to collect logging information from my devices. So in my device logger trait, whoever implements this should give me a function called name that returns a string, status that returns the device status, and error that returns the device error. Pretty straightforward. So when it comes to implementing this trait, I have my star tracker, then I'm going to implement that trait for that strut, and then inside of here I can call any private functions that aren't related to the trait but that I need to collect that data to fulfill the requirements of the trait. It doesn't really care how I'm getting that data, so I have access to the rest of the strut, and anything else I've implemented on it, I can call inside of here as long as I'm fulfilling these requirements of the function signatures. So then when it comes to actually using something that is implementing the trait, this is where generics can come in handy, and you can make some really useful functions. So I can create this log device status that takes any type, as long as it implements a device, this device logger trait, and it can call these functions. It doesn't really care what's going on behind the scenes, doesn't need to know what other traits are implemented by the strut or anything else about it. As long as that trait is implemented, you can pass anything into this function and it'll work fine. So we found this to be super valuable when it comes to abstracting behavior in our designs and for creating mocks of things like mock interfaces for testing. This is a tool that we reach for super often. All right, ownership and references. I'm going to cover this pretty briefly because you could spend 30 minutes or hours talking about how Rust ownership works. It's like a pretty deep hole depending on how deep you want to go. So I'm just going to give a couple different examples. So in this case, we have this strut device and then this function, trust me or not. I can see, based on this function signature, that I'm passing in a reference to my device. Now in Rust, all variables and references are immutable by default. So I know I don't really need to trust this function because this is a immutable reference, and it can't change my data. It can't null this reference or null this pointer because it's immutable. So I don't really need to trust it. It can just read my data. But if I wanted to make it mutable and allow access to the data, have a new function, trust me, really. So I have to add this keyword, mutable, or mut, and that will allow the function to actually access and write to the data in this strut. But because of the way Rust references work, they still can't null out this pointer, and the compiler will not allow me to pass a null reference into either of these functions. So I don't need to worry about null checking inside of my functions or outside of my functions because the compiler is not going to allow me to get into a situation where I have to deal with a null pointer. And honestly, it's really nice to not have to think about that. Okay, testing. Testing is really great, and they've done a good job of incorporating this into the language and the standard tooling. So in any source file, I can define a test module. As long as I put this little macro up here, it will know, okay, this is a module of test. Then inside of here, I can create however many test functions I want, and I annotate them with this. And these will not be built or run in the standard build, compile, run workflow. But if I use the Rust test command, it knows to go look for this code, pull it out, compile it into binaries, and run it. So the facilities are there to really encourage you to write test code and make it as easy as possible. This is not using any third-party library or anything outside of what comes really stock with Rust. All right, tooling. So tooling, I found, can really make or break a developer's experience. It really sucks to have to go find a separate testing tool and a separate documentation tool, and oh wait, I have to go find this other cross-compiler and bring these things all together and make them all work in the same environment. And Rust has done a really good job, or the community has done a really good job of trying to unify tooling and bring it all under one thing called cargo. So cargo allows you to do a lot of different tasks. When you create a project, you give cargo a manifest, and this manifest describes what is this project, what are the dependencies. Cargo knows how to fetch these dependencies, whether they are local on your file system or on GitHub, or if you don't specify either of those, there is an online manifest where it can go look and try to fetch these dependencies. So once you've gotten this down, you can use Cargo to build your code. And then once it's built, you can use Cargo to run your test and test your code. And then once that's done, you can even use it to run your code. And then when you're happy with that, you can use Cargo to cross-compile your code to whatever target, assuming it's supported by the Rust toolchain. And then once you're happy with all of this, you can even use it to generate your docs. So I love that I can just reach for Cargo for almost all of my development needs when I'm writing Rust code. All right, lastly, why should you hesitate about using Rust? I think for this audience in particular, the biggest hesitation will be with the overall maturity of the language in the ecosystem. Rust has been around in the production sense for about 3 or 4 years, which is relatively young compared to a lot of the tools that we tend to see in play in this industry. So that may be a hesitation for you. It may be a hesitation for your coworkers or the people making the bigger decisions about your project, but it's certainly something to think about. And if that's a showstopper for you now, maybe in 5 or 10 years it won't be, and this is something to keep an eye on. Toolchain availability. If you're using some super exotic hardware or operating system, there's probably a pretty good chance Rust doesn't support it. It does support a lot of the ARM platforms and some of the PowerPC platforms, and there's a whole group out there dedicated to providing bare metal support and kind of paving the way for that. But this is certainly something to think about based on whatever platform it is that you're targeting. The ecosystem, along with the language, is still relatively young, so it's not unusual if you're reaching for a library for it not to be there in the Rust ecosystem. Though, based on what I've seen in some of the presentations this week, that may not be an issue, as it sounds like some of us do like to write our own things or roll our own things when libraries don't exist or don't exactly meet the needs that we have. And lastly, I'm really not sure how the RTOS support is in Rust. I've seen some work on integrating it with free RTOS, but I really don't know how it would play with something like RTIMS or VxWorks. That's a pretty open question. At my company, we solely support Linux, so this is not a question that we have really had to answer. But if VxWorks or RTIMS is your thing, then this might be something you have to wrangle with, or maybe a reason not to consider using Rust. And that's all I've got. Thank you.
So you mentioned static garbage collection. So can you comment on Rust's memory management and determinism, how deterministic is, even if it's static? I don't know if I care if it's static or dynamic. I care that it's deterministic. So I don't know if you've encountered that.
So I can't say I've dug too much into that, so I can't really give you a good answer on that.
This is more of like a personal question. From someone who's done a lot of like C++, object-oriented, and a lot of Ada actually, for some reason. That looks like a combo of those two to me when I see what you're showing. I don't know, did you have any experience with Ada before you played with Rust? Or?
I looked at Ada just a little bit, but I haven't used it professionally.
When you're showing a lot of stuff, I felt like, man, this was a lot. I felt like the learning curve would be steep. How long did it take you to get comfortable with Rust?
I would say a few weeks, but I also had the benefit of I was enabled to just start writing Rust full-time and learning Rust full-time at my job. I didn't necessarily have to spend the time outside of work.
Okay, so you had the time to really get engrossed with it?
Yeah, once I kind of proved out that it was a feasible thing for us to use, they kind of set me loose to start using it.
Okay, thanks.
So with respect to the garbage collection terminology, I think where that terminology came from, there was a blog post about this comparing the way that Rust's ownership system works to a garbage collector that is handled at compile time. But that's not necessarily the standard way of working at it. It's not a garbage collected language as such, as people are used to.
Are you talking about Steve's blog post?
Yeah.
Yeah.
Yeah, so there was definitely some talk in the community about whether that was an apt metaphor or not, and I think the confusion that's caused here today might comment on that.
Yeah, it would be fair to say that Rust does not have a garbage collector, but in the same way that C and C++ do not have a garbage collector.
I had a question. Without like the determinism aspect and all of that, what kind of flight software have you used for, like, with Rust or created?
Like that we've written?
Yes, thank you.
So
wow.
we have a framework that we write in Rust, and it's our own internal thing. Well, I say it's internal. It's an open source framework, but we haven't done any like deterministic certifications on it at this moment.
So it's mainly like the framework that you guys have worked.
It's a framework, but it also consists of, yeah, processes and pieces, and there's plenty of code that could be certified, but we haven't examined it in that way.
Okay, we've got a question off the web over here. Hang on just a minute, and I'll get with you, and then we'll be ready to break for lunch. Okay, the question off the web is, I said I'll preface, I don't have a lot of experience with Rust. Are you able to have Rust use custom memory allocations, and how much of the standard library is safe to use in a real-time system? So the first question was, are you able to have Rust use custom memory allocations?
So I think the answer to that is yes. I've definitely seen people put Rust on microcontrollers where they had to have their own linker map that put things in custom places. I haven't done it myself, but I know there's a group that works on that sort of thing.
Okay, great. And the second question was, how much of the standard library is safe to use in a real-time system?
That's a good question. I don't know for sure the answer to that. I know there is the ability to turn off the standard library and still use most of the core language when you're operating in a like bare metal situation. But I don't know exactly what pieces are pulled out when you do that. Okay, and then last question.
You mentioned you wrote your flight software in Rust. And I'm looking at the Rust platform support, and they have different tiers of support. Tier 1 only includes x86. And now I was just wondering what sort of hardware you're running your flight software on, and how did you certify that hardware to run Rust well?
Right. So we run on the ISIS IOBC and the Pumpkin MBM2, and those both fall under the Tier 2 support. As far as like formal certification, we haven't gone through anything like that, but we've certainly done thorough testing on both of those platforms and not run into any issues with our software on them.
Okay, great. I think our speaker.